So let's welcome to lecture 24. Will be the second lecture in the module on multiplicity codes. The main topic for today, this one will be list decoding, univariate multiplicity codes. Particularly, hopefully by the end of this lecture, it's not a little bit of the next lecture, you will do the following theorem with you for party and Guruswami and Van. You do it independently. You can write it a little informally. For all epsilon, there exists a S naught. For all S greater than or equal to S naught, univariate multiplicity code over F with degree T, multiplicity yes, n points of evaluation is list decodable. Univariate and equal to 1. Decodable up to 1 minus P by Sn. Let's go. The before notice, today's lecture will possibly the most technical lecture in the entire course. It will be fairly, well, we really involve a lot of elements which we have seen over this one. It will be a bit slightly on the heavier side, but it will be very interesting. So there will be some parts which are trying to come up with new ideas and stuff to do, and some parts which are more parameter fitting to get the right numbers. I do not know if I'll be able to do both, so I try to do the former and the parameter fitting. Either I will certainly add it to the notes at the end of the day. And if there is, and if you want it, we can discuss it at the beginning of next lecture. Okay. So what is the problem here? So what's the problem in this one? Here we're going to be given n data points. So n data point. And what are each data point? Each data point is alpha 1. That's the field alpha 1 and beta 1, which is an S symbol long vector. So it gives you the S derivative. Given n such field, alpha 2, beta 2, alpha n, beta n, each of them belonging to SQ cross SQS. Then each beta is actually not a single element, but it's a whole tuple. It's the entire derivative supposedly. And what we want to do is want to find a polynomial that agrees such that on these points alpha i's, so for a large fraction of these points, if you evaluate the point at alpha I, the corresponding derivative sequence is actually beta 1, beta 2. Is a beta 0. In other words, you want to find on univariate polynomials P of degree less than or equal to T, such that what do we want? We're going to look at the number of data points on which the derivative sequence of P up to S at alpha I is equal to beta. That's the shorthand notation. P to the I is a particular derivative, P to the less than S is the entire set of derivatives from 0 to S-1. That at the point alpha I is equal to beta I, the number of i's for which this happens, say, is greater than or equal to some number. So T, D, N, S will all be parameters that we have to find out what is the choice of these parameters that will make the thing work. Right now, I'm going to say that we find that's the problem at hand. A priori, it's unclear if this is even combinatorially feasible. To what the question is, we want to make t as small as possible and still be able to do this. If t is less than half the minimum distance, then of course the Welsh-Berlekamp style algorithm will work. And I also mentioned if t is like close to the Johnson, what is the distance between the Johnson radius? And I said that a Gulfam-Sudan like algorithm adaptation will work. What we are hoping to do is push t even smaller than these factors. Push t possibly as small as t as small as which one? As small as 1 minus delta. That's what we want to do. And that's right now we'll keep it all variable, and eventually when we set parameters, we'll find out what's the best choice of t and And the idea behind it is going to be very much inspired by the Guruswami-Sudan algorithm. In fact, it's going to be taking the Guruswami-Sudan algorithm that we knew for read Solomon codes. We knew how to decode. It gave you a way to do decoding up to the Johnson radius. We take the same algorithm, and now that we have also the derivatives, what more can we do of it? So let's to begin with the warm up. Let's just recall the Guruswami-Sudan setting. In this case, each beta I is actually an element of Q. It's just the polynomial evaluation, no derivatives are given to us at this point. The algorithm, the GS algorithm basically had two steps to it. Step one was we find a polynomial Q that explains the entire data. Because we sort of we find a non-zero polynomial Q. This was in two variables in that case, x and y, such that two things were true, such that we wanted to have two properties. One, the 1D weighted degree of Q is less than or equal to D. That's the Q has this because and there was a reason why we did this that will be clear in the second step. That was great. So this is an explanation. We wanted a not too large a degree polynomial that had this property, and the fact that Q vanishes with multiplicity M at each alpha I beta M. Alpha I beta. For all I. And capital N and capital D are two parameters which were chosen by the algorithm. You optimally chose it therefore. That was step one. So this was an explanation for the data. So one the data came as n pairs. You now gave it an explanation by a Q. And step two. Let's say what step two does. Step two is basically find output all polynomials. All polynomials P of degree less than or equal to D, such that Q of X, comma P of X was identities. I'm saying it this way, when we did Guruswami-Sudan, we said factorize Q of XY, look at all the factors y minus px and output them. Okay, this will contain even spurious things in the list. You have to also sort of trim the list to throw out things which have less than t argument. But this contains the list. So this was the algorithm. That was the two steps of the algorithm. The analysis sort of went along these lines. So we needed to do both step one and step two. So step one went with, firstly, you needed to show why does step one exist. So step one, you will say that Step one, ideally, step one is just solving a linear system. So the way we wrote it was you find out the number of variables involved. So it's doable as long as number of variables. That's basically what one says. The Roman numeral 1 and step 1 tells you the number of variables that are involved. You can count the number of variables. That should be more than the number of constraints. And what is the number of constraints? For each n, we have the constraint that it vanishes with multiplicity m. So that itself is a bunch of constraints. Put all of them together. So it's n times the number of constraints to tell that a point, the polynomial vanishes at the point alpha I beta I. Put that, you wanted this, then you could do step one. So step one was always doable. So we set up parameters such that this is feasible. Then what was step two? Step two, we went stating that for every point of agreement. So firstly, we wrote it this way. I want to say why does step two work? Why do these polynomials P work? So there are some polynomials P which are close to the data, and we want to show that these polynomials are actually appear in this list. So somehow I have to show that every polynomial which has significant agreement to the data does appear as this. So let's pick up a point. So let P be a candidate polynomial. That has agreement at least T. Your connection is open. Then let's define this univariate polynomial R of x. Let's define it to be Q of x comma P of x. What did we then notice? When the way the step one was set up was for each point of agreement, alpha and beta I. If alpha and beta I was a point of agreement, then R had n roots at alpha. It was set up to have this property. Therefore, if there were T points of agreement, then you are basically counting with multiplicity. R has PM roots. But the degree of R was set up so that it's capital D. Now, if D were smaller than T times M, this would imply that R is identical C. And that's the rationale for step two. That's why this P of x will appear in that. Okay, this was the reason why we did this. Of course, then we have to argue that when we do this, okay, so this tells you that every polynomial P that we want actually appears as one such guy. But why is the list of polynomials of this type small? There we argued that every such polynomial has to appear in the factorization of Q of x comma y, and that's a small list, therefore it was small. We didn't bound the list explicitly, we just said it's a number of factors. So we will try to mimic these steps in our setting also. We will try to come up with a non-zero polynomial Q that explains the data. Now, how it explains the data? We have to work to find out what the corresponding condition for 1 and 2. And then the 1 and 2 will be set up such that a similar statement will be true. That is, you will have that for every polynomial P of agreement, you come up, when you plug that polynomial in, you actually get 1 to 0. So step one, we'll try to mimic these steps in the multiplicity setting also. And we also have to do one more step. Given such a Q, you should be able to tell how to extract the P. If you want an efficient algorithm, or if you just want to show combinable decodability, to show that the number of P that satisfy this property is small. For the purpose of lecture in class, I will not talk about algorithmic efficiency at all. We'll just do it and we'll just do the steps. Eventually, we can check that everything can be done in polynomial time in the size of all the everything put together. So we will not care about algorithmic efficiency. Our thing is only to show that the list size is polynomially large. For a suitable setting of PDS. So basically for a suitable setting of PDS and epsilon, we'll show that there is a setting of parameters capital D and capital M such that this list is. So that's going to be a game plan. So let's try to mimic each of these steps. So we'll take each of these steps and the idea is going to be extend. This is for parties group basically. First group is to extend the above plan to the multiplicity. Okay. So firstly, what should Q be? So Q is going to be, we're going to, let's find out how to, that we'll try to elaborate on step 1 itself. So step 1, what I want to do is, so Q there was a bivariate polynomial, one which took alpha I and the other which took the beta. Now here it's possibly not just a bivariate, it has to take all of beta. So we possibly will want to take Q of X to be some Y0, Y1, all the way up to say YR. And R is a parameter which we have not talked about yet. So question is, what is R? R. So there's a design choice. Now this one just like M and D where things. One. R can be any. So previously in the Boltzmann equivalent setting, R was just 0. You just had one additional variable. We can go all the way to R being S minus 1 because we have that many things. But notice when we write the multiplicity equations, we will be actually differentiating Q. The multiplicity, when you're saying Q has M root, we will be differentiating. So even though Q has only up to R variables over here, when you differentiate it, you will, this YR supposedly represents the R derivative. When you differentiate it, you will get larger derivative. So even though the Q actually involves only, Q only is talking about the evaluation of the polynomials and after the first derivatives. When you differentiate Q, you will actually get conditions on larger derivatives. And you want to ensure that all the conditions you get can be written in terms of the S minus 1 derivatives that we have. This is going to be a thing. So we will choose R such that all the derivatives that we can get. So R will be some number. The design choice we find out what R is. R can be any number between 0 and all the way up to S minus 1. Each of those we'll have to put those numbers. So, and each yi in principle will be, each yi in principle will be the ith derivative of x. That's what it will, at a particular point alpha, yi, then this is what we wanted to do. So first thing is, notice we have to do guarantee step 1. Step 1 has this whole, this one behind it. We need to check the number of variables. This is the main constraint in step 1. And the main constraint in step 2 is this. So we need to choose parameters such that these both happen. That is, the number of variables should be more than the number of constraints to solve step 1. Step 2, you will get the identity 0 only if the degree of the polynomial that you have is less than the number of agreement times the multiple. So we want to do these both. So let's. So we want to do that. Basically, when you say code is list-decoding. Yeah.
So is the situation that around any point in the ambient space, if I draw a ball of whatever radius, the list-decoding radius, there aren't too many things, or we want to make a statement of the form to start with the code word?
No. We wanted around any point in the space, if you draw a ball of this radius, there are only so many. That seems like a stronger requirement than what, because you received word is only obtained by corrupting a real code word. But we would I made this same error when I did the proof of Elias Basilico. We assumed this latter definition of list decodable. For most applications, you actually need the other def. So let's look at the unique. So even let's go to answer your question. Let's actually use the problem in the unique decoding setting. So what do I want to ask? Unique decoding, you know that if you make less than d by 2 errors, you can recover. But the other statement is also true. Around any point of radius d by 2, there is at most one code word. There might be 0 code words, there is at most one code word. Now, to do the Hamming bound proof, what was the Hamming bound proof? We drew around every code word a ball of radius d by 2. And we wanted to say that this is a what do you say? These balls are disjoint. For that, we needed the fact that for every point, there is at most one code word of radius within d by 2 of it, not for everything that comes from a code word. You look at it there, we needed it. So, and Elias Basilico was the same sort of. So, for all these sort of applications, I will need the stronger property, not just for corruptions of the code word, but for every point in space, you have this property.
So the reason I was just mentioning is that this whole thing of variable is being more than the number of constraints.
Yeah.
The only reason you need that is because of this property. Because there are many times when if you know that you got a corruption of a legitimate message,
yeah,
you can mostly show that there is a queue that works. It's just a question of whether your algorithm is finding that same queue or not. Like the reinforcement setting, a queue that always works is y minus m of x times x minus alpha I times the error locator.
Yes.
So, but I guess you need this to sort of say there is a non-zero queue,
even for an arbitrary point, there's a non-zero. Yeah, right, fair enough. Yeah, so your difference, the original Welch-Berlekamp algorithm, many times it is set the second way, which assuming it's a corruption of this one, but you can state it in the other way also. For any received word, you can draw this. Yeah. Ideally, I want yi to be pix. So firstly, we need to count the number of variables. What is the number of variables? So notice that. So typically, I expect the degree in yi of q. What will it be? It is basically going to be d minus I. Because that's what I'm eventually going to plug in this. When I set it to d was when I eventually plug in p of x, p1 of x, p2 of x over there, the degree of yi is going to be no, sorry. What I want is I want to ensure that this is the case. That is, sorry, this is not what I meant. I meant the weight of yi in q should be d minus n. In other words, I must be looking at what I call the 1 d minus 1 d minus r weighted degree of q should be less than or equal to d, because eventually I'm going to plug in, and in y naught I'm going to plug in p, y1 I'm going to replace it by p to the I. Therefore, this will be the degree of r. This will be the degree of r. That's why you remember the 1d weighted degree was defined to be this way. So this is what. So that is for each monomial x power e. X power e, y0 power e0, y1 power e1, yr power er. We want e plus summation p minus j going from 0 to r ej to be less than or equal to. So, in particular, we need to be able to count. So there is this. We need to be able to count. We need to get an estimate on the number of such monomials. This is to, if I just find out the number of variables, I need to do this. This is for now. This is all of this is for the number of variables. Now let's do the number of constraints. I come to the field. This is what I need to do. We'll figure out how to calculate the number. This number is not an easy number to calculate. It's a number of points in some lattice. It's a number of integer points that they are weighted some like this with utmost capital D. Then you want to estimate the number of. Then you want to look at the number of constraints. What is each constraint saying? Each constraint is stating that Q at this point Q. Each constraint is n times the number of constraints for stating of the following. Q has multiplicity m at point alpha beta. So it's n times that. Now I have to find out how do I express this. In the case of Guruswami Sudan, this was what did we say? We will assume we basically wanted to say write down Q in the basis x minus alpha, y minus beta. X minus alpha to the power I, y minus beta to the power j. This is a valid set of so Q is a degree to Q is a bivariate polynomial. Therefore, a potential basis for it is with things of the form x minus alpha to the power I, y minus beta power j. There's a unique representation when you write it in this fashion. Once you write it this way, you wanted that the coefficient of every x minus alpha to the power I, y minus beta power j for I plus j less than m should be 0. This was the multiplicity. We want to do the same thing over here. We want a multiplicity. So what am I going to do over here? So let's look at, so we have this, so take a specific point alpha I, beta I. Suppose it were a point of agreement, then we do know that P less than S of at alpha n equals beta n. Is equal to this vector beta n. Let's construct this polynomial Ri of x. Let's define this polynomial Ri of x. I'm going to define it to be summation beta I, the jth location of it, x minus alpha I to the power j, going from 0 to s minus. This is basically, if beta is correct, what is it? Ri is defined in such a way such that observe that if P agrees with data at alpha I, beta I, then we have that P of x is identically equal to Ri of x mod x minus alpha I to the power x. That's basically what it means. The P and Ri of x map agree in the first lower order s minus 1 coefficients. This is the same thing as saying that these are the right derivatives. Okay. So this is an important thing to keep in mind so that we start. This one. Now, if this happens, now suppose I differentiate P as well as R a particular number of times. Suppose I differentiate it once, will it still continue? Suppose I differentiate P once and Ri once. Will this still inequality hold good? It S will reduce by 1. So in particular, you could say the following. You could say that for all j, anything less than or less than s, if I differentiate this j times, this will be Ri differentiated j times mod x minus alpha I to the power s minus j. And that's just because of the following, and that's just the proof of that just follows from the fact that P of x is equal to Ri of x plus some polynomial q of x into x minus alpha I to the power s. Now, when you differentiate this j times, this will get differentiated j times, this will get differentiated j times. And you want to make sure that this one still x minus alpha I to the power s minus j here. So this one will keep reducing. That's why you'll get out here. As I differentiate this, they won't be equal all the way. They'll be equal only up to lower order one. Okay. By the way, all of this exercise is being done to express the fact that I need to express the constraint that Q vanishes at this point alpha beta with multiplicity M. So I'm going to come up with some weird monomials. These are not, I call them monomials, but these are weird polynomials. I'm going to now, once again, I'm going to come up with a base. There, what was the basis of polynomials we came up with the Gurusomi thing? X minus alpha power I, y minus beta power j. This was the basis which we said, and we said that this spans the entire thing. And then to express multiplicity, we said all the lower order things are seen. We are going to do the same. We're going to come up with another basis, which is going to make this clean. So the basis is going to be, I want to say the following is a basis for F. Going to be on the form x minus alpha I to the power e product yj minus rij x to the power ej, j going from 0 to r. As you range over e0, E0, E1, E2, E2. These are all. I want to say, look at these set of polynomials. These set of polynomials I claim firstly is a basis. And is that clear that it's a basis? Rij is exactly this time, the guy I defined here. So Ri is this derivative polynomial. Rij is the jth derivative of the Ri. It doesn't matter what Rij is for this. I want to claim, irrespective of what Rij's are, you should be able to look at this and see that for a fixed I. For a fixed I. So the following for each I, we have this is what I want to do. For all I, the following is the basis. I determines. By the way, if this had not been there, you would have agreed with what I said. This should have been obvious. If this had not been there. But this, I claim, does not change much. You will just keep lowering the degrees of y each time you take the largest monomial in the y's, you remove it out using this some expression of the form, and you will just keep lowering the total degrees in y, and that can be handled inductively. So I want to claim that this is, it should stare at this long enough, you should be able to see that this is actually a basis for my entire.
They all have the same leading terms.
They all have distinct leading terms. So that shows they are independent. But
every monomial goes up as a leading term of
one of these. So yeah. Why am I writing this? This is a nice basis to capture multiplicity with respect to alpha I beta. So suppose I want the polynomial Rx to vanish with some multiplicity n. That's the whole thing, is to capture the fact that Rx goes. So when I plug in R of x, I'm going to plug in. I'm going to plug in place of yj, p, the derivative of pj. That's what in R of x is going to happen. So what do we want of, what do we want? We want Q to vanish. We want for each P and an agreement point alpha I beta I of P with the data. We want R of x defined to be equal to Q of x comma P of x to vanish with multiplicity n. The whole condition is being set up, is reverse engineered in order to get this particular condition. Huh? So in particular, if you expand this guy out in the basis x minus
P, you mean P, P1, P2.
no. For each polynomial, this P, for each P,
R Q is an R plus 1 variable, R plus 2 variable.
Sorry, so what I mean by here is P less than or equal to R X. Now, when I plug in this guy over here, this vanishes identically to 0. So, what does that mean? That when I write this in its monomial basis, possible at the point alpha I. So, in other words, when I write it in the monomial basis x minus alpha, the power of x minus alpha I to the power j, it must have no monomial of the term of degree less than x minus alpha I to the power n. Everything should be there. Now, the point is, at a point of agreement, we have that Rij of x is equal to Pj of x mod x minus alpha I to the power s minus j. This is what we observed before. Therefore, what do I want? In order to have this condition, I'm going to reverse engineering the multiplicity condition. Huh? Yes. This would be E over the way of the ER. Is that you're taking? Yeah. E0 of the ER. Reverse engineering multiplicity. So let's call this the basis BI. What does it mean? That when I write it in that basis, the coefficients of or the following set of monomials, coefficients corresponding to E0 to ER, such that E plus summation S minus J EJ is less than M. These are all the guys which will actually, if you now, because I want to plug in this over there, this will give me, so if I plug in RJX and PJX, I get that term will give me multiplicity S minus J. And that's being multiplied by power EJ. So if all the coefficients of all these terms, coefficients of the basis elements corresponding to these guys, where E plus summation S minus J EJ less than M, these all are 0. Then I get, if they are 0, then R of X has multiplicity at least M at alpha. Let's clear this a little longer. So, okay, is that basis right? Okay, that's a basis. So I'm going to write Q of X in this basis. And now in this basis, I'm going to plug in PJ or the PI of X. I'm going to plug these values in. And now, so now it's become a univariate. It was an R plus 2 variate polynomial. It has collapsed to a univariate polynomial in X. But when the collapse happens, look at every monomial, look at the monomials. What is the multiplicity of X minus alpha I in that? If for a particular monomial, for a particular monomial, I'm going to call this monomial, but not a monomial, for this basis element, which is what? Which is x minus alpha I to the power e yj minus rij x to the power ej, j going from 0 to r. The corresponding multiplicity will be, what is the power of x minus alpha that divides this? It will be 1e from this. And each of these has multiplicity s minus j. Therefore, it will be the multiplicity will be exactly E plus summation s minus j times ej, j going from 0 to r. Each of these this monomial, when you if you plug it at the data point, this monomial will be divisible. So suppose this monomial, this number had happened to be small t. Then this particular monomial for Rx is divisible by x minus alpha I to the power t. And basically now I'm stating that every monomial which has t less than m all have to have coefficients 0. That will ensure that R of x will have only things of the form x minus alpha I to the power t with the t's are larger than m, larger than or equal to m, and hence you have multiplicity at least in. Sir, you don't see happy.
Are we are we proving something, or are we trying to set up?
We are trying to, I have to express what the multiplicity comes. So eventually, I'm going to go reverse engineer the process. I want to ensure that R vanishes with multiplicity m at an agreement point. That's what I want for this one. Now, what should be the conditions in step 1 in order to ensure this? And the whole thing is being reverse engineered in order to get this. So
for every such, so suppose this bag is some, I don't know, let's call it B X or something. So I mean, like for a particular,
so let's call this BIM.
Okay, so this is BI. So what we want to say is that given any R of X,
no. So R of X is not given to us. It was not given to us. We want to say that the R that you get this way will have multiplicity at least m at this data point. Now, so this data, notice we don't have P's in our hand. We only have Rij's in our hands.
We have Q in our hands.
We have Q in our hands. We want to set up Q. We have BI. We have the basis in our hands. The BI's we have in our hands. So so at this point as agreement, I can write Q of xy in this basis.
So for every choice of y, you have a representative
basis, and I will write it in that basis. Now, once I write that basis, now suppose this point happens to be an agreement point with some polynomial p. Let's see what happens to that polynomial p. Well, that polynomial p, when you plug instead of y1, y0, y1 to ir, you plug in p less than or equal to rx. We know because it's an agreement point, we have this condition. We have this condition. So even though we didn't have pjx, we can, as long as we are looking at x minus alpha, we can assume that the pjx is actually equal to rijx mod x minus alpha I to the power s minus j. So let's look at a particular monomial. Let's look at this monomial. Now, what happens when I plug in p into this? Here I'm plugging pj of x. Pj of x is going to have multiplicity s minus j with respect to x minus alpha. X minus alpha I to the power j is going to divide this quantity. X minus alpha I to the power j is going to divide this quantity. X minus alpha I to the power s minus j is going to divide this quantity. That is what is the total power of x minus alpha I that you get. This monomial will contribute. Now you are ensuring that.
So you now want to say that any of these monomials where the total power that you can guarantee is less than m, you're just going to exist at low coefficient.
Rather, the only monomials which will appear will all guarantee that the power is more than m, at least m. That's what you want. There is the monomials which will only appear will be the monomials which will ensure you that the power will only be at least m or more. Anything that can contribute to m less than m, you just force it to be non-zero.
So, in other words, to state it differently, you are going to look at all polynomials q of x comma y0 to yr with that weighted degree, such that it can be written as a linear combination of just these.
No. So it's all polynomials of that, but when you write it in this basis, these coefficients should become 0. So it's a weird thing. It's the same thing what happened on the Guruswami-Sudan thing, but I'm going to do this. So I'm going to write all polynomials in that, but now write that polynomial in this in the basis bi. For each data point, go and write the polynomial in the basis bi, and then say these polynomials in that representation. That's all I'm doing. All of this is just to count the number of constraints. The number of constraints is basically the number of such monomials. For every such monomial times here. So the number of constraints is basically this. So what I claim is, if you recall, the number of variables was the number of such guys. The number of variables was exactly, so let's say like the number of variables was exactly equal to the number of E R, such that E plus we are going to 12. We are going to the class. No. Hari, it's going to happen in Hari's office. It was one person. I thought Hari told me the classes always happen. Okay. So the number of variables is this. This is what we have seen. So let's keep that one, and we want to estimate this. Now, what have we seen? So the number of we needed to estimate this number. The number of constraints. The number of constraints is n times number of E naught up to R, such that E plus summation j equals 0 to R, S minus j, Ej is less than. These are both very similar quantities, it's different weightings, different targets, and we need to get an estimate on both these numbers. And we want to ensure that these numbers are such that one of them is more than n times the other one. All of this discussion, all of this basis could be precisely to say, I'm going to write it. I'm going to count the number of constraints. Of course, you have to do this efficiently also. I don't care right now. It's going to be just, I'm going to do. So let's first now try to we want to understand this object. So let's take a small diversion from this problem and go to understanding this specific question. So counting. Number of integral points. Under that is what we are interested in. So let's take this problem of its own. So suppose we are working in k dimensions. The dimension for us was r plus 2. The number of points are living in r plus 1 plus 1, and you are given a weight vector. W1, W2, Wk. These are all, let's assume they are non-negative integers. The weight vector. And you're given a target P. And let's define n, so NWT to be set of all A1, A2, AK, such that summation Wi, AI is less than or equal to T. And what we are interested in is NWT. You have a class here? Yeah, you have a class on Friday, no? No, but I started in the class on Wednesday. Oh, you started to move forward. Okay, what we share is this number. When we see, we will try to prove upper and lower bounds for this. Because we need both an upper bound and a lower bound. We have to consider constraints and variables. We need to show that n number of constraints is more than the less than the number of variables. So we both need an upper bound and lower bound for quantities of this form. We prove it and then we go and plug in the upper and lower bound for it here. How am I going to prove this? So we will for any integer, say n, let just be L be the set of all x1 to xk such that summation xi is less than or equal to. By the way, everything are non-negative. These are not all integers, these are just these are okay. But this is a number which we know quite well. What is this? What's the size of this? L plus k choose. This is just the number of monomials or number of k-variate monomials of degree at most here. So that's L plus k choose. Now let's also define this box BA1 to AK. Think of A1 to AK as a potential solution to NW. This box is just going to be those x1 to xk such that Wi ai is less than x is less than strictly less than W ai plus 1. So it's a box in the. So it's x's which are lying between, each coordinate is lying between. So this is for all I. It's a box, it's closed on one side, open on here, the other sides. That's what the box is. And notice these boxes, as you range over A1 to AK, it's a complete covering of the k-dimensional space. Now we make two nice observations over here. Let's take any x in PL. In particular, it is contained in some box. There exists a such that x is contained in P of A. But now furthermore, and notice that that box A will have to lie in. Sorry, I'm going to call it P of P. That box, that A will lie in NW. So take a point in XPT. It is going to lie in some box. Now the defining point of that box, the bottom leftmost point of that box, all the values are less than WAI. Therefore, summation xi is less than P. Therefore, summation WI is also less than P. So therefore, you do have this. So what does this give you? The end result of this is if you take the union of all A's and NWP of the balls in of the boxes corresponding to A. This certainly contains PT. Okay, so that's people with me so far.
So given any x, it is present in some box, and the index of that box happens to be in NWP.
Yeah.
Okay.
Therefore, in particular, if I
run over all, if you run over all possible boxes that are indexed from NWP, it must cover all of x.
All of P.
The summation AI omega I, or firstly you are keeping all AI as 1 and looking at summation omega I less equals to 1.
Yes.
And now you are just keep increasing AI from 1 to more than any number and just looking at the points. How summation omega AI will this will is equals to L in the same condition, right?
It didn't follow. I didn't follow.
So the first PT set is summation omega I less equals to P.
Yes. No, which first PT? PT, there's only one PT.
Yes, summation omega I less equals to P. All such points, set of points.
Which one are you? I didn't follow.
So the set PT is the summation omega, summation xi less equals to.
Yes.
So we are looking at all such points where summation xi less equals to, so the corresponding weight is the AI we can take as 1.
No. WIs are given to me. I don't have a WIs are given. So basically, so the picture is sort of like this. There's some weird. This is the quadrant, and there's this weird weighted guy that you're looking at. We are sort of covering the space with boxes.
All boxes are completely under the.
No. So we are saying that
Lowermost point is under.
the lowermost point is under them. And it says that those points cover all the points. That's basically what it is. So all the lowermost point, the leftmost point, if you contain them, they cover, those the corresponding boxes are full covering of everything underneath. That's why you have this single point.
So boxes corresponding the leftmost point of the box is they take all boxes in leftmost underneath it.
Yeah.
Take all of the boxes, the exact line will be over the.
Yes. But the leftmost point of the boxes which are under the line are exactly my NWT. So that this will give you one. This will give you one direction of the, because notice further direction, the size of each box is a fixed size. What is the size of a box? No matter what A is, the size of the box is the product of the WS. So this, what does it give you? It gives you that NWT into product WI is greater than or equal to P plus K choose. That's one direction to go. So let's put that. So we can get P plus K choose K divided by 1. I want to change the other direction also true. What do I want to say? Exactly the same picture. I want to say P. Take all the boxes of this type. Take their rightmost point. I want to say what do I want to say? I want to say P. I want to say the same thing on top. P plus summation WI is contained in union A belong to that is, I'm going to draw another line over here. Certainly, this line, this is the line corresponding to T. This is the line corresponding to T plus summation W. Claim is all of these boxes are necessarily under this. Therefore, you get the other input. You get out of this, you get NWT times pi is less than or equal to P plus summation WI plus K choose.
Is that A bar? It belongs to PT implies there exists A bar.
Yeah. Dropping the waves completely. Yeah. That's the direction I have P plus summation WI plus K choose K.
That would be also.
Huh? Yeah, I mean, A bars and A I'm not going to. If I remember, but too many papers are like that. That one. Okay, now let's return the problem. So now we know step one. So step one is basically this is going to be step one. Find a non-zero cube such that the 1D, the non-zero cube in f of x, y naught up to y r, that 1D d minus 1 up to d minus r weighted degree of q is less than or equal to d. And for each I n q when written in the basis bi have zero coefficient for not going to be about that one. Okay. And step one is guaranteed to find a cube if what we have is as long as n is let me just number of constraints is less than number of variables, and we know how to write this. We know how to write this. We can write down the equations. That's the step one is taken care of. Let's go to step two. So at the end of this, what do we know? Let P be a polynomial that agrees with P points of the data, P data points. Then we know that R of x written as q of x comma p less than or equal to R x. R of x has at least p times m roots with multiplicities. Step one was completely reverse engineered in order to ensure this. Hence, if D is less than Tm, then R is identically zero. Because and notice the degree of R is less than or equal to D, the variable. So this is more the analysis of step two. So step two will actually be find every polynomial P of degree less than or equal to T such that Q of x comma P less than or equal to R of x is identically zero. This is what we want to do instead. Notice this is no longer as clean an equation as we had before. There it was Q of x comma P of x. It was bivariate factorization, y minus P of x. Now it's this whole thing. So we actually have to go. First we see one. There are two things. So we have to first show the number of such p's is a small set. And furthermore, if you want to do it algorithmically, I will also tell you how to extract this p from this. All I have is Q of x comma. I have the polynomial, I have the multivariate polynomial Q. From that, I need to extract the polynomial. But this is not multivariate factorization, no? Because the if P satisfies this, why is you don't know the way why it's unclear. How do you I don't see how to capture this as a factorization. So if Q of x comma P of x is this one, then I know how to write that as well. This one I don't know how to write it as where it was clean, we could do that. But for all you know, this polynomial could actually be, I mean, if P satisfies this, your Q could just be irreducible. Don't see there anything that's possible. Q could be irreducible. Yeah. Q could be. I mean, unlike the bivariate. Yeah. So I need to, so actually what we will do is we'll actually give a process to do this, and the same process would have worked over there also. So we'll actually do a first, so we'll go into how to extract the P from this. There we had appealed to factorization. Basically, we were going to go into the innards of factorization. What did factorization do to obtain it? We will go and obtain it. So the rest of this, the next part of the thing, we have to set better. We still have to do all this big parameter setting. I have to choose V, M, P, so that the constraint is there's a number of variables, D is the TFM. That's where all the finally you'll get the achieve goals of the capacity. But I just want to say that we can do certain things. So the next part of the next 15 minutes, what I will do is I'll give you ideas about extracting P from Q of x. Why not? That's going to be helpful. Okay. I won't do this in its full. This one, I'll give you all the ideas for it, and if you write it in detail, will be this one. But I'll give you all the ideas. Give out all the ideas. So what is P? Basically, I want to find all polynomials P of the following form. P as of the following form: e power I, x power I equals 0 to P. Basically, I need to lay my hand on the coefficients P. But what do I know? I know that if I plug this polynomial P of x into that, so that is find P such that Q of x, P of x, P1 of x, P of R of x. This is identity. We need to find P such that all P such that this happens. This is a polynomial equation. So of course, one thing you can do it, you just write down the polynomial equation, write down this, plug it in, you have a question, you can try to solve it. Unfortunately, it's not a linear equation. They will be, because Q has all sorts of weird things, it won't be a linear system. That's all. You get a very nasty this one, the way it happens. By the way, this is the main difference between Koparty's algorithm and Guruswamy-Wang's algorithm. Guruswamy-Wang will further reverse engineer Q such that the Q the thing over here will be a linear system in the PX. That's the main difference between Guruswamy-Wang and Koparty. They will further put conditions in step 1, so that's a linear system and you can solve it faster. We will not put those conditions, we will actually solve it even though it has larger degree in 1. Okay. Notice this is a polynomial. So we had a polynomial Q of x, this is we have this solution. This is an identity 0 polynomial. So in particular, it is 0 mod x square. You can go mod any other polynomial and still it will be 0. Now, why is this a useful thing to do? we will try to extract the polynomials of p. So suppose I go mod some x power k. K is a small number, k is some number less than d. Notice that it will, you don't have to care about coefficients of p larger than pi's for I larger than k. They will not up because in the mod those they will appear with a x power x larger than it. That's not fully true because I'm going to take derivatives. So which coefficient will not appear? So if I take the value, if I go mod x power k plus r, because I'm at most taking r derivatives, you will know that if I go mod up x mod up to x power k plus r, I never have to. I can write down. If I go mod x power k plus r, I don't need anything more than more than I, which is greater than k plus. So what we will do is, what the idea behind this is going to be, we are first going to say, let's, for the first few terms, for the first r terms, let's get, so we'll start off with, let's guess P0, P1, P2 up to PR. Let's just guess it. Basically, the algorithm is going to go over all possible settings of P0, P1, P2, PR to be in some arbitrary points in F2 to D R plus 1. Now, we are going to keep on and then say, given this, can I make one more step in the process? Can I, and I know that this is 0, and I know, suppose I managed to guess it correctly up to a particular point, I'm going to ask, can I guess one more step? And this is, and basically what we're going to do is, we are going to guess this and find find pi for I greater than equal to r, and how are we going to do that? That is inductively, we are going to, given P0, P1 up to Pk, we will find Pk plus 1. This is what we are going to do. And we'll see, is there a way in which we can find Pk plus 1 uniquely out of this? So let's write the polynomial. So there are whatever polynomials here. Let's write. So P of x is Pkxk plus P less than k of x mod x bar k plus 1. Everything else vanishes off. And suppose we do have the equation. Suppose we, so what do we have? We have q of x, p less than k of x, p less than k of 1 of x, p less than k r of x. We know this is 0, same mod. Which mod should I have to go over here? K plus 1 minus r. That right? Okay. So suppose we've gone up to this point. So we have managed to find it. So we have found out these. This is the same as fine. So if I had gone mod x bar k plus 1 minus r, I need not have gone up to P. P only these p's, only this information of the p's matter. I don't need any further information. So suppose we have, so the way.
Taking the derivative, then calculating.
But they are the same thing, no, because p plus q, the ith derivative is pi plus qi. The derivative of the sum is the sum of the derivatives.
Which term? So the first truncation is actually k plus 1 minus. The second truncation is k plus 1 minus r minus 1. So the last truncation will follow. See, I mean, okay. So it's a question of when you write p sub k and the first derivative.
Yeah.
How many terms does it have? What is the degree of the polynomial?
So the The degree of this polynomial is x power k.
No, and so p less than and I mean you're so what is the third thing in the bracket mean? Did you truncate and then take the derivative or did you are you looking at the less than k part of the first derivative?
The less than k part of the first derivative.
Yeah, okay. That is fine.
I was thinking.
What is the other thing?
The other one could be that you first truncate. You look at the lower degree terms of p, and now take its derivatives of order 1. That will have degree k minus.
Yeah, okay.
So that's what.
No, your question is whether I have to write this because it's pk less than 1 x or p
This
less
is the
than
same
1
as p. I mean,
it's a difference between these two.
yeah. But if you replace the second guy with the first guy with p less than k plus 1, then they're going. Then they're going.
Which one?
If you first look at the first k plus 1 terms of p, and take its first derivative.
Yeah.
That's the same thing as taking its derivative and taking the first k term. Take first k terms of the derivative.
Yeah, I know follow. But what did I want to do about all of my? The second one, what I want to
So
do.
okay, now
I don't want
this is what you want, then all these subscripts are actually k plus 1 minus.
So I want
Right. Or rather k minus.
I want the first guy certainly. I'm going to go larger and larger. So what I want is that that's right. P less than k plus r minus 1.
That is just without any derivative.
Am I right about it?
So we want to get k plus 1, right? The k plus 1th term.
No. I want to first say what I have, and then I want to go to what I have. When I differentiate this, what will be? So what is?
I have k plus r minus 1. Then you will get the. I mean, yeah, the minus 1 is truncation of the RF derivative of p.
The k minus.
So you look at the RF derivative of p, and just take the first k minus 1. That's what you do.
Okay. Now okay, you guys have to make me continue.
No, maybe let's just do the first. So what have we guessed so far? We have guessed p naught to.
So basically what I want to say is
let's try to find p r plus 1. Everything else is the same thing. The indexes will change.
the indices will change. Yeah.
So let us focus on p r plus 1. So in the first term, p r plus 1 shows up. So let's not truncate anything. Suppose we just write all the things without one.
Yeah.
In the first term, p r plus 1 shows up with power x power r plus 1.
Yes.
The second one, p r plus 1 shows up with power x power r.
Yes.
Blah blah blah. The last one, it shows up with degree 1.
It shows up with degree 1. Yes.
So which means if I go mod x squared, okay, it shows up only in the last guide. Everything else is going to become.
Fair enough.
And now you have a linear equation in p r plus.
Okay. Fair enough. Okay. So let's.
Yeah.
This is answer the thing. So that's how economics is also. This is exactly what they do in. They invoke the algorithm. So that's good. So what do we want to do? We just want to do the.
I just want to go mod x squared and see what we do.
Let's find this. Let's find. Let's find. Let's find PR plus 1. So now let's write the equation Q of x comma P P less than or equal to R x. Write this. Let's write this mod x square. What are we going to get? This will be x. Here in the P of x term, I
We only get P naught plus C1.
this is all that number.
Yeah.
Here it will be
It will be P1 plus P, like 2 P2x or something.
P1 plus 2P2x.
Right? And it will keep going like that.
And
The
you
last guy will be PR minus 1, something times PR minus 1 plus something else times P. Times it.
So there will be there it will be some by there will be some alpha. There will be some alpha times PR minus 1x.
No, no,
So
no.
PR
PR
minus
minus 1.
plus beta PRX.
Right.
This is congruent to 0 mod x squared. Okay. Okay. By the way, so this is in Q. So it's still not yet. Q is still a high to large degree polynomial. Now what we will do? So, by the way, this is also similar to this one. Q has two large degrees. Now let's apply Taylor on.
We can just do the following, right? What are all the degree 2 terms? That degree 1. So the only thing you care about is what is the constant term here and what the degree 1. Oh, that's only the
That is clear. That is clear. Yeah.
yeah. Sorry. Yeah.
So I'm going to think of this as Q of x comma, this is point P0 P1 something plus x times this one. Is that how I want to write it? Yeah, this is how I want to write this. This will exactly be. Let me write it from this one. Let me write it as. Let me write it as Q of 0 comma P0. 0 P0 P1 this term plus x times this. This is Q0 this guy. So let's call this point. P3 was a bad term, so P tilde and this is P tilde. So what you get is Q of P tilde plus dou Q by dou X, and this will say this is P prime. Dou Q by dou X times the X
Dou Q by dou X at P tilde times X. Right?
At P tilde times X plus summation j equal from 0 to R dou Q by dou Y Yj at P tilde times this whatever P, there will be a corresponding.
Yeah, P prime J is important.
P prime J X. This is what we have.
Mod.
Mod X. Now notice in this expression there is only the term corresponding to j equals r has PR. All the rest have lower order terms. This is the guy which I know because this is what would have happened if I had gone mod x. I have already know this. So this is the term I know. There is exactly one PR over here out here, which is I know this is equal to 0. So can I extract it? I can extract it provided the coefficient accompanying it is non-zero. So in particular, what will be so can extract Yeah, you have control. Yeah, yeah. This is commented.
I think it is automated.
Can extract ER if its accompanying coefficient is non-zero. So we need to know what is its accompanying coefficient. Now the accompanying coefficient is characters is dou q by dou yj dou yr at p tilde. Okay, it's not just that, there is a binomial coefficient that keeps coming. There will be a binomial coefficient. Like I'm right, it is k plus r to r. In our case, it's just r plus 1 to r. This will be the binomial coefficient. This will be the. There are two things to notice about this. So this is for just extracting r plus 1. And notice the same process works for even larger, exactly the same thing. And notice even the large, exactly the previous thing, this term will remain the same. The binomial coefficient will change. The binomial, so that's the powers coming from above. This guy will always be dou q by dou yr p tilde. And this will be some binomial coefficient. So the proof will work as long as firstly the characteristic is large enough to ensure that all these binomial coefficients are non-zero. If they are non-zero, so you choose the characteristic such that it's larger than the degree of the polynomial that you have. So these binomial coefficients will at most be the degrees that are coming out. So you choose, the first thing you choose is choose characteristic of P large enough such that all the binomial coefficients are non-zero. You never get that.
So these lower bound becomes only on A.
Huh?
Is characteristic lower bound becomes only S.
No.
It's
D.
D.
All the way.
So the prime has to be bigger than D plus R.
D plus R. Yeah. So it doesn't. So it's open to ask if multiplicity, univariate multiplicity codes over low characteristics. Do we have anything? We don't have a algorithm. All algorithms currently fail, and they fail precisely because of this reason. Complex binomial coefficients come, and we don't know how to handle this.
Does the answer extraction step?
This step,
It's extraction step.
the extraction step. Extraction. So this is non-zero. But that's not sufficient. I need dou q by dou yr at p tilde to be non-zero. Why is that non-zero? Now, let's look at that as firstly as a formal polynomial. Dou q by dou yr. You can ask, is that zero at all? If it is if it were non-zero, there exists some point p tilde at which it is non-zero if its degree is less than the field. So right now I'm expanding around the point or the origin, 0, 0, 0. You will expand around that point and the same proof will exactly verbatim go through. Huh?
One point where
As long as it's 1 point, so basically you will move the origin to that point and do. So right now I'm doing mod x square. It becomes mod x minus alpha squares or something like that. It will be, I'll be going in that basis and I will be able to expand. So I won't get p in this basis, I'll get p in that basis and I'm. So that's not an issue. Question is, what happens if this becomes identically zero? Huh?
Because then Q won't be the smallest point.
So we haven't yet used the fact. Now, then there is, if that were identically 0, that means you wanted P to satisfy a particular Q. Dou Q by dou Y is a smaller degree polynomial with the same P satisfies. So just go into, so we need to show. So dou Q by dou Y if this were identically 0, that means when I am plugging in the polynomial X, P less than R, X, this is identically 0. That means this is the candidate guy. You replace Q with this guy and do the whole. So you, and for it, do the same process and keep doing it this way. So at some point of time, you will have to end up with some non-zero dou Q by dou Y, or it goes down to degree 0 and there's nothing to extract.
So you're basically saying that for the minimal degree Q, this procedure will work. If you choose Q to be the smallest degree polynomial that satisfies your constraint.
Fair enough.
Then once you get the first R term, you can get
Yeah, but the point is, our algorithm doesn't give you the smallest degree.
No, because you're talking. You're the got it.
Yeah. So okay, that's basic. So the basically now that says the list. So one. Yeah. So whatever so the list size. So basically, if this is 0, work with dou Q by dou YR instead of, or equivalently do. So the point is, so the list size is basically your initial guess. That's all of the list size. That Q per R plus 1, you guess those guys, and next thing. Some guesses might not, you might extend some illegal points. Later on, you can prove them. But once you have guessed it, it tells you how to deterministically go forward all the way up to the mean. That's basic. By the way, this is also the factorization algorithm. Exactly. Cancel lifting. What's up? Okay, I've gone very fast, right? So what I will do in the beginning of next lecture is I will put the parameter. There are 3 parameters which we have. We have to put them together. I put them at the bottom of, by the end of today, I'll add them to the notes, post it. You can either look at it in the beginning of next lecture, or you can just look at this and this one, and this will get you things. The nice thing about it is it gets you, you can go as close to capacity as you want to. Oh, the reference for this is Coparty. So it's now Coparty should be there it's there on the web page. There's both Coparty and Guruswami Van will also do this. Guruswami Van does a different argument for it. Basically, they ensure that you don't get, they make the system, the step 1, they further say that they have this property, but they say the degree of y in each of yi is always 1. The degree of all the yi's is 1. Therefore, the only difference between this and Guruswami Van will say, Guruswami Van proof is find a Q of the form A0x plus A1x y y0 plus A2x. It's called the A of x. A of x plus A0x y0 plus A1x y1 all the way up to ARX y-R, and that's they solve this. So the things become cleaner here. That's all. This is and also all your counting and all of this becomes much cleaner. But you realize this only after doing all this. So I thought I would rather do this and then say, okay, if you do this, one of the homework problems will be, which I have not yet added in, will be basically doing it this way. If I bring this right at the beginning, it's unclear why such a Q should even. The reason is because it helps you solve the system. Everything becomes easier when you do it with the counting number of Qs, the multiplicity, all of them become extremely simple with the Qs of this kind.
We might ask, can we do this for this form? It's Sudan? No, we can't do this for this form. Only in the multiplicity code we can do it. I don't know how to do this.
We find you of the following form and in several steps become easy. Not this.